Alright, so we've been able to successfully look at the different dimensions of space. We've explained 1D, 2D, and 3D space, and how we'll be able to go on from there if need be. The next thing we're going to look at is the nature of space, and there are two groups of these. There are two different ways to look at this. The first pair is what we're going to tackle now, which is absolute and relative space. From the name, it should be able to kind of get an idea of what this means. Absolute space was proposed by Isaac Newton, the English mathematician, physicist, which, as the name implies, as absolute space implies, his idea is that space is unchanging, rigid, permanent, and absolutely universal. So Newton believes that space is universal, absolute, unchanging, and permanent. So along those lines, so you can imagine what his idea basically is that for everywhere, for everyone, and across all places, the same space can be used for wherever you are. So think of it as a permanent grid on the backdrop of Earth. That's Newton's idea of space. That space is absolute, it doesn't change, it is fixed, and it shouldn't care, or it shouldn't matter where exactly on Earth you are. Relative space, on the other hand, is proposed by a German mathematician, Gottfried Leibniz. I hope I spelled that right. Gottfried Leibniz. And his idea is the exact opposite of Newton's. He says that space is not fixed, it is dependent, and space is subjective. For basically every calculation you see now, relative space is the assumption that is used, and this means that everything you do is taken with respect to an origin. Everything you do is taken relative to an origin. So if I'm plotting a graph, I will have points with respect to my origin on that graph. If I'm taking the length of a football pitch, if I'm measuring the length of a pitch, I'll take an origin to be one side of the pitch. So that means I'm not working with one fixed space on the background. I'm able to create, or we're able to create in physics, our own origins as how we need it to prevent unnecessary coordinates. So that's the difference between absolute and relative space. Absolute is mostly philosophical and theoretical, but relative is more practical method that we use now. Over to the next pair is Euclidean and Non-euclidean geometries. They are named this way after a certain mathematician by the name of Euclid. He lived around 300 BC and was one of the founding fathers of mathematics and geometry. He laid down, on his book, on his theories of geometry, he laid down about 5 postulates as to 5 bedrocks, 5 things that must be fulfilled to make a geometry, Euclidean geometry. So that's why they're called Euclidean. They're named after Euclid. Some of them are, all right angles are the same in everywhere on that space. A straight line can be extended indefinitely in both directions and it will remain straight. And the last postulate of Euclidean geometry is what's called the 5th one. Postulate 5 is the parallel postulate. So the actual statement of this postulate is may not be intuitive to understand, but in essence, what he means, or what is being said, is that given a line, let's call this line AB, and a point that is not on this line, let's say point here, let's call this a point K. Given line AB and a point that is not on this line, only one line can be drawn through K, that's this, that will never intersect B. What does this mean? If I have a line and another point that's not on this line, there is only one other line I can make that will pass through K and still be parallel to AB. So that's what we mean by Euclidean geometry. You have probably almost always only definitely encountered Euclidean geometry. It's the geometry of straight lines. So when you draw your graph with your two axes. That's Euclidean geometry. When you have a cube, or when you're working with simple three-dimensional space, that is also Euclidean geometry. So that is what this means. But non-Euclidean geometry kind of sort of took rise with the advent of Einstein's general relativity. We may get more into that later. But what this means is that some of these postulates do not hold. And there are two main categories of non-Euclidean geometry. The first one is spherical. And a very wonderful way to look at it was to imagine a set of coordinates on a globe, on the Earth as it is. So given this, you definitely have a north and a south pole, a top and a bottom. So given this, you see that lines do not remain straight in the traditional sense of the word. They curve around the body of what makes the space, in this case Earth. So they no longer remain straight, and some of the postulates of Euclidean geometry end up getting violated. So that's what makes spherical coordinates. And the second type of non-Euclidean geometry is hyperbolic, or I like to call it Pringle's geometry, because it actually looks like a Pringle, if I can get a good sketch of it. So something like this, then comes up a bit, then curves, then this comes up a bit, and then down. Okay, yes, this should be good. Yeah, so if this were a little bit more rounded at the edges, it would very much resemble a Pringle. But this is based on hyperbolic functions. That's why it looks the way it does. And the lines, this is actually called a saddle point. So that's how the geometry of this works. Two of these are not exactly straight in the word, but they are still coordinate systems, just they don't align with all of the postulates of Euclidean geometry. Okay.